So today's stuff is YouTube quality of service, right? So we'll talk a little bit about YouTube. We'll talk about quality of service, right? This is our other dip into technical stuff, right? And again, I'm sure a lot of you people think that we covered a lot of deeply technical stuff, but I promise you, we're just all the stuff we covered past like the first couple Facebook lectures, we're really just skimming the top of the iceberg. All right. So here, I'll fire up iClicker. We'll eventually do some questions. All right. So yeah, today's we'll get a little bit technical, but I'll try to keep it in a way that you can understand. And I'm sure you shouldn't have much trouble. All right. It just looks so messed up. Okay. Weird and slow. I'm not sure what's going on there. Hmm. All right. I'll try that one more time. We'll see. I don't think I lost anything. We'll try again. Hmm. All right. Well, we'll get back to. I don't know what's going on with the iClicker people. Maybe their servers are down or something. All right. I think that went. Okay, great. Cool. Okay. So here we are. We got this quality of service, right? All right. So what we'll cover, typical problems that get experienced, latency, jitter, and the solution, buffering. Buffering isn't a problem, but its topic needs to be covered. Talk about how you measure it, how you manage it, and then eventually some stuff about YouTube and how they manage their own systems. Okay. So first, YouTube, right? Everybody knows about YouTube. It's about 20 years old now, founded in 2005. Google shortly thereafter acquired it. I remember it must have been in 2007. I was a PhD student here and I talked with one of the other PhD students. I was like, hey, I just found this cool site where you can like watch old music videos and stuff. And it's called YouTube. And he's like, yeah, I know about YouTube. So anyway, I was already a little slow to the party, I guess. Anyway, like most of those kind of sites, it gets most of its revenue from advertising, but a little bit from other sources. There's paywalls, there's subscriptions. For a little while, well, we'll talk about that. Last I checked, and this is within the last 12 months, #2 website in terms of visits, so second only to Google, and an astonishing 37% of worldwide mobile traffic, right? So it is the site you go to when you're watching something on your phone, I guess. Rough number of videos they have, about 1 billion. It used to be higher, used to be 2 billion, but I think they got rid of some videos that nobody was watching and some others because of copyright issues, and they pruned it from about 2 billion to 1 billion. So anyway, very big site, very big operation. Now, quality of service. Okay. So quality of service is certainly a term that you've heard before, right? You've heard it in terms of cellular networks. Verizon will claim they have, the best quality of service, and T-Mobile will come out and say, well, we have the best coverage. Maybe you guys better quality of service. Fine. So what it means, it's a term that's generally applied to any kind of network system or application, and pretty much means how well it's working around the two big factors: data transmission rates, how much data they're sending over the cables, and reliability, how continuous the flow of data is, right? Those are the two big things around quality of service. However, because different applications have different needs and different users have different needs, it's also kind of a composite catch-all advertising buzz phrase like big data, right? People say our quality of service is great, right? But what are the exact breakdown of the components of how that is? So, for example, typical users, right? Email is one of those things I mean, speed is always nice, right? But if you're sending somebody an email, you're more important that it gets through complete and intact as opposed to getting there fast, right? Email is one of those things that you don't expect quite instantaneous response. Usually, if you get the message within a minute, that's probably fine. Likewise, with images, same thing. Speed is always nice, but if you're sending an image somewhere, you would like it to have it be, complete and correct. You don't want to have like little bright spots, little fireflies in the background of the image, stuff like that. On the other hand, with video, because video generates a continuous flow of data and often at a frame rate above what human eyes can distinguish, right? Human eyeball capacity is around 40 frames per second. So anything much faster than that, the humans aren't really going to notice the difference. So speed and reliability are great, and in most cases, more important than getting everything there complete and correct. Because if you got to skip a couple frames, you can still watch the video, right? You'd rather have the video play continuously than, have it stop to capture a couple frames that you wouldn't notice anyway. So quality of service, overall means how well the system is working in terms of network communication, but it can mean different things at different times. Different factors can be more important. Okay. Now, streaming video, right? A video data stream is just a set of packets, where the packets contain elements of the images and, probably an audio stream as well. So the set of packet transmissions with a specified order, and depending on how you've set it up and what kind of compression technology you're using, one packet might be able to encompass many frames, or one frame might have to be broken up over many packets. But at any rate, the video stream is just going to be a set of packets like we talked about the other day, how the internet works. And all those packets are going to be sent in sequence, and they're going to arrive in sequence, and your browser is going to unpack them and construct them into a video feed and start playing it. Okay? Now, way back when, let's see, about 25 years ago, say, maybe a little more than 25, a lot of people had shitty dial-up connections, right? And a dial-up connection in those days was maybe 33 kilobits per second. If you had a nice dial-up connection, maybe 57.6 kilobits per second. But what that meant in practice is if you wanted to download and watch a video, it was going to take about 20 to 30 minutes. If it had, like, you'd get some little video like this big and, it'd be like a 2 or 3 minute, like a 3-minute song. It'd take like 3 minutes to play. Or it'd take like 3 minutes, 20 or 30 minutes to download. It would take 3 minutes to play. So the ideal with quality of service is simply that the user gets that data to play the video as fast as those new frames are needed, right? So roughly speaking, if the video takes 3 minutes to play, as long as the data for that video can start playing pretty much instantly and packets can arrive over the course of that 3 minutes, it's good. You're not going to notice the difference. The video is going to play just as well as streaming as it would if you had it stored locally on your hard drive. Okay, so that's the goal with this kind of setup. Now, there are some general streaming concerns. Number one, waiting for the entire video download can be slow, right? Now, these days, connections are obviously far faster than they were in the late 90s, but if you're talking about downloading a whole big video like in 4K quality, that could easily be a couple gigs, and that could take a little while, right? It's not going to take hours, but it could take a couple minutes to download, and you don't want to wait a couple minutes. You want to start watching that right away. So that's one problem. You'd prefer not to download the entire video before it starts playing. Number two, what happens if some of those frames arrive out of order, right? If some of the frames take different paths over the internet, some of the later ones arrive early, some of the early ones arrive late, then it's going to be maybe a long time before your video can even start to play, right? Because your file is going to not be able to be properly constructed. And finally, what if a few frames arrive very late or never? All right, so we'll talk about these issues, but the basic principle of YouTube is that instead of downloading the entire video file, you download chunks of the file at different times. All right. For those of you who are leaving, hurry back. We'll do a question in a few minutes. Okay, so typical quality of service problems. Number one, slow video starts, right? You want to start playing the video right away. It's going to download a big slug of data in order that it can do that. but for some reason, the download starts off pretty slow, and that sucks, right? That's a typical problem. A common source of that is simply you're trying to download too much data at the start. Second, choppiness. You have a lot of starts and stops during play. You ever experience that? You start watching a video at one point in your house, it plays fine, right? You're watching it on your phone or laptop or something. You move to another room in the house, and suddenly there's a lot of walls and stuff between you and the router, and oh shit, your signal quality sucks. And now, the video really stops playing. And so it pauses, it hangs up for like 10, 15 seconds while it's loading more data, and then it starts playing again. And finally, bad quality. And that tends to be linked to the choppiness, because one of the things you'll often see in practice is that if a video stream can't deliver high quality video frames, it'll say, well, I'm going to deliver you low quality video frames, and at least I can deliver them to you. So you'll see, that it'll go from being a very clear picture to very chunky looking. Okay. And all of these issues essentially have the same root cause, and it's that there's too much network traffic relative to the available capacity. The technical term for this is network congestion. That means when you have a network with, that's basically operating the way it's supposed to, but has heavier than expected usage. Somewhat different from the problem where, you have the network is perfectly fine. It's just the position between you and the components of it can't transmit that much data. But that's still too much network traffic relative to capacity. So in general, if you want to think about it as a concept, network traffic results from the number of users times the number of apps they're using times the amount of data per app. So as things have gotten bigger over the last 25 years or so, right? Internet-wide, not only internet-wide, but even in any organization, any household, more users using more apps, and the various apps use more data than they did, network traffic goes way, way up. And just like cars on a road, when network traffic exceeds the system's capacity at any point, there's going to be some kind of delay. There's only so much data that the network can push through per second. And if people are asking for more than that, well, things are going to go horribly wrong. All right. Well, at least things will slow down. All right. Let's do a question. This is a good break point. All right, let's do some YouTube stuff. All right, let's do number 6. I'm screen sharing. All right. Let's take about a minute, make that work. I click your question for those of you just arriving. All right, I'm going to call it. Ding, ding, ding. Okay. All right. So, correct answer? Let's see what survey says. Interesting. All right. Well, correct answer is, in fact, none of the above, which at least was the most popular answer. So that's something. Okay. So we'll go over these real quick. Number 1, U.S. government guarantees that networks will meet federal quality of service standards. They do not, right? The federal government does not do that. So there you go. There are, however, industry standards for various things like cellular traffic, 4G, 5G, that, and, various flavors of LTE as well, that, people, the cell providers have to provide in order to qualify as being those. If not, then, you know, I guess they'd get hit with some false claims lawsuit, but it's a different thing. Second, internet is fully owned and operated by the US government. I don't know how 14 people put in that the government owns the internet. I mean, 14%. That's, I hope you all clicked the wrong button there, right? The government does not own the internet. Okay. And certainly the US government does not own the worldwide internet. And finally, C, US government mandates use of standard communication protocols. Strangely, that was popular. That was the whole thing we spent a little time the other day talking about, right? That basically protocols happen from the ground up, that different network groups said, hey, we're doing it this way, you're doing it this way. Let's figure out, you know, how we're going to do it if our networks join together. And basically over time, standards get built without any sort of government involvement. All right, so correct answer, none of the above. And if you got it without guessing, well done. Okay. All right, so let's move on. Ooh. Okay. Now, sharing network capacity, right? Obviously, most networks are in a situation where there are many users trying to use the capacity, and the network has to manage that in some way, right? They have to say, you know, basically device A, it's your turn to go. Device B, now you got to wait. So if two devices, A and B, are trying to transmit over the same channel at the same time or over the same piece of hardware, whatever, those transmissions are going to interfere with each other. So you need some kind of scheduling arrangement to say A is going to go first, B is going to go second, or vice versa. Okay. Now, if you have a low utilization network, right, meaning a network that's not very busy, unregulated transmissions might be fine, right? So think about it like if we're all just mobile devices, right? Every human here is a mobile device, and transmitting is like talking, right? If hardly anybody is ever talking, then chances are when you want to talk to somebody reasonably close to you, you can say the stuff you're going to say and the other person will be able to hear it, right? But if everybody in the room is trying to talk at the same time, if the network is busy, then probably nobody's going to be able to hear much of what anybody else is saying clearly. Okay, so if the network isn't busy, maybe you don't need that much in the way of transmission scheduling. But of course, as the network gets busier, number one, that kind of interference becomes common, right? It happens all the time that whenever you're trying to talk, somebody else is also trying to talk over you. Number two, network traffic gets dominated by retransmission attempts, right? So instead of just saying, oh, I lost that message, I didn't hear it, the other person's going to say, what did you just say? And you try to repeat again. Well, that means, you know, a lot of time in the network is going to be spent sending data that's already should have been sent. And finally, because the network gets full of that kind of retransmission attempt data, then any new traffic tends to get backlogged because you were going to go ahead and talk about something else, but you can't because you're still stuck on your original topic. Okay, so this is the problem in a busy network, right? In a busy network, these are serious problems. And to an extent, you want your network to be busy because it means you have to pay less in hardware costs to supply, you know, a given amount of, to handle a given amount of traffic, right? So low utilization networks, yeah, they're nice for the users, but relatively speaking, they're also very expensive, right? Because a lot more hardware per individual user. All right, so sharing network capacity in practice requires some kind of transmission scheduling scheme, right? You have to make an arrangement of basically how the different devices are going to take turns transmitting. All right. Now, basic ideas with a lot of them are, number one, a device won't transmit if another device is transmitting. I don't know why these things don't get saved. I make these changes every semester, and somehow I fail to keep them. Okay, transmitters don't transmit if another device is transmitting to the same receiver, right? If two devices do transmit to the same receiver, they're going to wait a while before transmitting again. And the gap between transmissions is going to get longer over time. And that roughly tends to make the amount of transmission in the network balance out against the available network capacity. So this is the part where I'm going to give you something real good. And you'll all be like, damn, I am glad I went to lecture today. Okay. So suppose you have two devices. All right. Let's move you up a little bit. Okay. Okay. Two devices, A and B, are trying to transmit to a device R, but A and B cannot directly communicate because they are too far apart. Okay? There's a basic problem here. So, two wireless devices trying to transmit to the same point. All right. Now, I'm going to draw in a little bit of arcage here so you can have a rough idea of who's transmitting where, right, and what the extent of it is. Oops, shit. All right, something like that. And then for B, we'll do blue, I guess. Okay. Blue can just barely hit R like that. Okay. So those are the transmission areas of the two devices. Now, the part that I'm going to give you, it is entirely possible that while you're eating Easter dinner or whatever weekend dinner you may have with people who are funding your education in whole or in part, they may ask you, hey, what have you been learning in college lately? And I'm going to give you something good. Okay. What I'm going to give you is what is called, I'm going to move you out of the way, is the binary exponential backoff scheme, or the BEB, for network transmission scheduling. Okay. And so it's very possible that your grandma may ask you, what are you learning? And you say, well, just on Thursday, we learned about the binary exponential backoff scheme for network transmission scheduling. And chances are your grandma will be so intimidated, she'll be like, oh, damn, that sounds cool. Good. Or glad I'm getting my money's worth. Right. But on the off chance that your grandma used to work in networking and she actually knows what the binary exponential backoff scheme is, it's a good idea to know what it is. Right. So she might say, yeah, I remember. I used to work out at the Aloha station back in 1970, and we were pioneers in that stuff. Remind me how that works again. And you can say, well, very simple. Number one, you have a handshake process, right? Which is that, suppose we're going to take the case where A is trying to transmit and is not sure whether B or some other device is also transmitting to R. Okay, so A sends a RTS, request to send packet, to R, which basically says, hey, is it cool if I send you some information? If R is not busy, it will return a CTS, or clear to send, packet back to A, and A will begin transmitting. Okay, no problem. A knows that R isn't busy, so great. Okay, however, if R is busy, it will not respond. And A will wait or back off for a little while before asking again. Because asking over and over again at short interval is like, like you're an impatient 3-year-old is really rude, right? So you tried, you didn't get a response, so you wait a while, okay? Any successive backoffs will be twice as long as the previous one. Thus, binary exponential backoff. That's binary exponential backoff scheme. And again, the point of all this is trying to roughly match the transmission rate against the available network capacity without requiring a lot of coordination, communication between devices in a network that might already be very busy. Okay, that's the idea with the binary exponential backoff scheme. So if you want, you know what, I'm going to save this as a thing and I'm going to paste it because you might need this. I don't know. Binary exponential backoff. Okay, I'll upload that later. Cool. Okay, so there are, of course, a bunch of different scheduling schemes. You might, for various reasons, decide to try one or another. Maybe you want to minimize the average delays or risk of interference, right? That you want to get traffic through the network fast. You want to push through as much data as possible. Or you might have a bunch of mobile devices installed in some remote location for environmental monitoring. And because it's a big hassle to get in there and change their batteries more than once a year, you want to have their batteries last as long as possible so they deliberately don't transmit very often. So you might choose a scheme that extends battery life the most, or you might also include a scheme that ensures different users have equal opportunity to participate in the network, that basically everybody is guaranteed a certain amount of data if they want it and the network isn't otherwise busy, right? So there are a bunch of other ones. Point of this course is not to get deep into that, of course, but just to understand that within networks, you need some kind of order, and there's a lot of different ordering schemes. Okay. Now, the other three things, latency, jitter, and packet loss, right? These are some things that typically arise in, what's the word I'm thinking of? In busy networks. Let's see, how is our time? Yeah, let's do another question. All right, because this is a good, I want to, well, I don't have to explain myself. We're just going to do another question. Okay. Did you guys do the JavaScript exercise yet in lab? Or was that for next week? For next week? Yeah. All right. Okay, we'll give you 11 then. Even though we haven't covered web apps, a pretty good chance. This thing is, no matter where you put it, it's always in the wrong spot. Okay. All right, so there you go. Question 11. Here it says web application, but you know, it's the same question if you scratch off the word web. Why do applications use standard as opposed to custom interfaces? Right, you just made it back in time. All right, that's good enough, I guess. All right, look at those people. Okay, correct answer. Oh, well, that's unfortunate. Okay, correct answer. Why you use standard as opposed ones? Weirdly, you could make a case. I would pick the best. I would pick the second best answer as to thwart security threats. You can make a case for saying that standardization has some help with that, but the answer is this: if you have a standard interface, then you don't need to design a bunch of custom interfaces. It's less work, right? If you had infinite time, right, and you could just crank out interfaces like whatever, then yeah, go ahead, make all the custom interfaces you want and specifically design them for any particular application pair. But in the real world, it does take a little bit of time and effort to make a good interface. And so, it's basically it's an effort versus benefit kind of situation. So, all right. Well, let's move on. Okay. So talk about these three video problems: latency, jitter, and packet loss. And I'm sure you've all experienced them, right? Latency is basically where your network is moving slow, right? So I say here transmission delays. What it just means is you figure your ping should be something like 20 milliseconds, but it's more like 2 seconds, right? Takes a long time for anything to happen. Second one is jitter. Jitter is variability in the delay. So for example, a lot of the time your ping is really good, right? Data gets delivered quickly, but every now and then it's like it stops or gets really, really slow. Okay. And then packet loss is pretty self-explanatory, right? Simply some packets in the stream fail to arrive. And then either you have to restart the file load or the application times out, whatever. Okay, so we'll talk about how these things happen. This is kind of important stuff. Okay, and we are going to use an example of two users getting data from two things at YouTube. Okay. Okay, so here we have a switch. Well, I'm going to specify it's switch hardware. So it's just a little piece of hardware there, kind of like a router. And here we have cables, and every one of the cables has a 1 gigabit per second capacity, right? That's how much data they can send, every one of those. Okay, and on the right, we have user 1. On the bottom, we have user 2. And at the top, we have server 1. And at the bottom, we have server 2. Okay. So let's talk about latency first. Suppose user 1 and user 2 both try to access a server with their data requirement let's say 0.4 gigabits per second. Will they get their full data rate? What do you think? Yes, no, yes? They both want to get 0.4 per second. Is that going to be fine? What do you think? Is that a yes? Sounded like a yes. I wasn't sure. Sounded kind of like a Billie Eilish song in the back. It was like, yeah. Oh shit, he knows who Billie Eilish is. Okay. Yeah, I have kids. Anyway, all right. Yeah, 0.4 gigabits per second is not a problem, right? Because the system can support 1 gigabit per second. Okay, it's like a water pipe that can push through 1 gallon per second, and you're in aggregate asking for 0.8 gallons per second. Not a problem. Okay, but suppose both users want more data and they try to pull 0.8 gigabits. Well, we'll do I guess 0.8 will work. I can do the math. 0.8 gigabits per second each. Grand total 1.6 gigabytes per second. Okay. Now, it may be possible that if they're both doing it on parallel, right? If they're both doing it in parallel, if user 2 is getting it from server 2, user 1's getting it from server 1, there could be enough capacity in the system to handle that. But if they're both trying to pull that much, where'd my cursor go? There we go. If they both try to pull that data from the same server, there's not enough capacity, right? Because capacity is only one gigabyte per second, and they're trying to pull 1.6. So what's going to happen? Well, they will probably each get about 0.5 gigabytes per second, right? Right? No reason yet to assume user one has more or less priority than user two, right? So what's going to happen is they're going to experience that as latency. This will be experienced as latency where, right, any transmissions take about, if you do the math, take about 60% longer to arrive. Okay. So if you're trying to download a file that should take like a minute to download, could take about 1.6 minutes. If you're trying to, have some interval where you think, you should get like 16 frames, well, you're probably only going to get about 10 frames, something like that. Okay. That's what's going to happen in this situation. So that's where latency comes from. Too many users trying to pull too much data over a cable with, finite capacity. Okay. All right. So that like I said, that's latency. Now, we're going to back it up a bit. Now we'll talk about jitter. Okay. Now we'll get rid of this. New example. Suppose user one is an ordinary user like you or me. Okay. And most of the time they, well, let's see, and they're requesting 0.3 gigabytes per second, which the system can easily accommodate, right? There's 1 gigabyte capacity. They're only asking for 0.3, not a problem. Okay, but suppose user two has super high priority, and every now and then they join the system and request, let's say, 0.99 gigabytes per second. Okay. And because they are super high priority, they claim that much. Let's say they actually receive that usage. Okay. So what's going to happen, most of the time, user one, they're doing their thing and everything seems fine. But this second process, whenever they pop in and they claim almost all of the capacity, right? Whatever user one's doing, suddenly it's going to go from being, okay, things are good, to like, hey, this is a lot slower than it used to be just a second ago. And then when user two's gone, things bounce back to normal, right? Now this can happen. This is jitter, right? Variability in latency, because there's always some latency, but jitter means, it's not stable and predictable. It's just, it kind of happens. This can happen from high priority users or high priority applications, right? If you have a Windows machine, you've probably experienced a thing where you get onto the internet and Microsoft decides it's really important to do a big, update download. And for like a minute or two, you basically can't do anything on the internet because that download is going on, that kind of thing, right? So high priority applications or temporary surges in user population, right? So again, if for a little while there's a whole bunch of users joining your system, right, this can happen because, in aggregate, even if they have the same priority as you, if there's a bunch of them requesting data, you're going to feel that too. Or applications with short-lived but intense downloads, right? So if, for example, you're trying to play Fortnite in one side of the house and your little sister is on the couch watching YouTube and she's basically doing the, couch surfing version of YouTube where she watches a video and it downloads a big slug of data for that. Then she switches to a new video because that first one sucks and downloads a big slug of data for that. that may negatively impact your Fortnite experience. And then if, you're my son, you yell at your sister to stop switching videos, right? All these kind of things cause jitter. Okay. Last one is packet loss, right? Packet loss, simply some transmissions don't arrive. Well, this switch hardware has a little bit of memory. So I'm going to push this down here for a second. Why is this hard? Whoa. Weird. Okay. So, and we're going to do here memory. All right. So imagine you have this same situation where there's a flow of packets going out, right? It doesn't really matter from where, right? We'll say red is going to user one, and maybe blue is going, some of them to user two, some of them also to user one, whatever, right? There are all sorts of packets in the network. Now, imagine if both of these devices are requesting more data than the switch hardware can actually process, okay? For example, imagine that user one is requesting a lot of data from both servers, right? Requesting 1 gigabit per second from both servers. Well, what could happen is that the two servers are each sending their full 1 gigabyte per second to the switch, and the switch gets overloaded, right? And so what will happen is over time, there will be an accumulation of packets at the switch. Now, it can easily happen that, it often happens in real life that switches do experience this sort of short-term accumulation of packets. And so they hold them for a split second, and then when the situation clears, they can pass them on. But if the buildup happens for a long time, eventually that switch hardware's memory can get full, right? It can be all full of packets. And then at that point, the next packet that goes in will either A, get kicked out because why? Because the switch hardware doesn't have enough memory to store it, or B, the switch hardware will have to drop one of the older packets in order to make room for the new one. So that's how packet loss can happen. All right, so those are three common, problems, and that's a simple, I guess, description of how they work. Okay. Next thing, buffering. So to smooth out those kind of problems, a lot of video streaming applications use what's called buffering. Buffering is simply where you download a big chunk of data before you actually need to play it. So if you start watching a video on YouTube, you'll often see it downloads like 30 seconds or a minute of data, like within the first few seconds of playing. And then even if you disconnect from the internet, your application can keep on playing that video while, it has still buffer left. Okay, so buffering addresses those kind of streaming problems that if there's latency, you won't experience it on the packets that you've already downloaded. Same thing with jitter, right? Unless the jitter is really bad and it lasts beyond the end of what you have buffered as data. Even lost packets, if they don't get transmitted the first time around because maybe you disconnected from the internet, if you reconnect, as long as the buffer is still playing, right? If you get those packets in time to be played before the buffer runs out, it's all good. Okay, so that's why these applications, they use buffers. All right. Now, again, just to talk a little bit about quality of service, right? Emphasizing that a lot of people think about quality of service in absolute terms, right? Like more data is better. More data per second is always better. But you can also think of it in terms of, is your quality of service good enough for your intended purpose, right? And this mirrors the way that people talk about quality in manufacturing, right? So basically, you can talk about objective quality. So for example, I have a phone. It is a low-end phone. When I went to get this one back when, the lady at the phone store said, well, we have the new iPhone for, only $10,000. And I was like, well, I was thinking something kind of lower end. And she's like, well, we have a Samsung that's like $10 a month. And I was like, do you have anything cheaper? And she's like, this one is $7. It's like, yeah, now we're talking. Okay. my wife is a big fan of the iPhones, right? She likes having one, whatever. You know, I guess if I were out there dating, I'd probably want an iPhone just for that, but I'm not dating, I'm married. So, yeah. Anyway, but they both call, right? They both call fine. They can do like all the same stuff. I'm sure hers has some advantages, but for what I do with my phone, my cheapy one is absolutely fine. So, its performance is good enough to meet its design target, right? And I'm happy with it. So boom, quality of service is good. And the same thing, yeah, I mean, quality of the product is good enough. And same thing in quality of service, right? If it's an email application, quality of service doesn't need to be instantaneous because it's going to take you a while to read that email anyway. Okay. Uh, Other stuff, peak to average ratios, right? One of the things you often see in real world networks is that networks will have short, temporary, but really intense bursts of traffic, right? Where things get really busy for a little while. And, you know, back in the early days of the internet being a household thing, what you would often see is a massive increase in traffic at, you know, shortly after 5 p.m. when people started getting home from work. So that sort of thing is something that you have to cover in your networks as well. Now, the basic question around that is how much trouble is it causing you? Is it worth it to massively over provision capacity so that you can make all of those users happy? Or is it better to have them wait a little while? You know, it's kind of like the same thing as going to a call center, right? It's nice if you don't have to wait very long to talk to somebody, but if they make sure that the call center has a lot of people available all the time, that's going to increase costs for them, and that's going to be reflected in product prices. So no free lunch. In the mid 90s, right? Typical delay times to getting on the internet in the evening, something like 20 minutes, half an hour were pretty typical. Now, you know, the internet never really gets congested like that. All right. Video quality, right? So we talked about this, about how streaming video should deliver packets in time to be shown, right? Basically the same as if you were watching it from your own hard drive. And interestingly, though, YouTube doesn't use what is arguably the more technically perfect option. So that's kind of a follow-up to this whole, you know, quality of services being good enough. So here we bring in TCP versus UDP. Anybody ever heard of UDP? Nobody? You guys have heard of TCP, though. Yeah. TCP is ordinary internet, right? Rough number, something like 96% of internet traffic is TCP. UDP is the main alternative, right? Pretty much the other 4% that's, you know, not administrative traffic is UDP. So these are these two different plans. This is the difference. So TCP is connection based. And by connection based, that means you build a stable path from the source to the destination, and every packet that's part of a message follows that same path, right? It's very easy then, you know, the first device sends out the first packet, then the second packet, then the third packet, and they all arrive to wherever they're going in sequence. UDP, on the other hand, is connectionless, right? So I'm gonna draw a picture. A very simple network picture, though. Okay. So here's source, here's destination, and here is option one, option two. Okay. Source and destination, right? Oh, okay. So with TCP, what'll happen? The source will either pick the path S1D or S2D, and the entire packet series will get sent over that path. Okay? Also, there will be handshakes at each hop where the receiving device verifies that it received a packet, so the sender knows it's okay to send the next one. All right, so the source will send packet 1, maybe to device 1 here. Device 1 will confirm back to the source that it got it. And then the source says, oh, great, now I can send you packet 2, and so on. Okay. And then when 1 sends a packet to the destination, that same handshake is going to occur so that device 1 knows that it can send the second packet to the destination. Okay. With UDP, is basically fire and forget, right? So each packet gets sent without regard to how previous packets were handled, right? So packet 1 might go source 1, destination. Packet 2 might go source 2, destination, and back and forth. Okay, as local conditions dictate, right? Basically, at the moment that you send it, the system is going to say, hey, what's the best way to send this packet? Let's look at network conditions and figure it out. Okay, so the short version of this, TCP is more reliable, but a little slower. Okay, UDP is faster, but a little less reliable. Okay, the difference used to be bigger, like, you know, back in the 90s and the aughts, the 00s, but now are not that different because handshakes take only a split second and reliability is generally higher. Okay, so these days there's not that much of a difference between the two. If you send a message over UDP, it's probably going to get to where it needs to be, and it's probably not going to get there much faster than TCP. The internet still mostly uses TCP because if the speed isn't that different, you might as well go with reliability, right? A lot of applications need that, but you know, it's not a night and day difference between the two. Okay, so performance comparison. All right, this is all that. Now, we talked about how YouTube uses the less technically perfect option. Well, for true streaming video, be like listening to the radio, right? If the moment passes when you're listening to a song, it's just gone. So there's really no need to worry about reliability. You just send the packets out there and hopefully they arrive in time to get played. Okay. But YouTube uses TCP instead because number one, as we'll talk about momentarily, YouTube isn't true real-time streaming anyway. It's basically sequential download of file segments. The videos get broken into a bunch of little files, and YouTube sends you those little files. Second, some systems can block UDP. Firewalls are often like a little bit sensitive about UDP because you can't tell that packets all are arriving in a sequence. So basically the firewall on your device, when you send a request to YouTube saying, hey, good people at YouTube, you know, please send me this such and such video, and then that packet stream starts arriving, your firewall looks at that and says, oh, here's a packet stream from YouTube. You made a request for that. Okay, cool, right? But with UDP, there's not that much information, right? Packets might arrive out of order, and depending on how strict your firewall security settings are, they might look at that and say, oh, we don't like the look of this packet stream. We're just going to block it. So YouTube didn't want to deal with that, so they chose to use TCP instead. Okay. There's also a hybrid name called Quick, which if we had more time, I'd talk about, but you know, TCP and UDP are not the last word. Quick is kind of this happy middle ground between the two that Google uses in its internal systems. It tries to be almost as fast as TCP and almost as fast as UDP and as reliable as TCP. So basically it tries to be the best of both worlds. All right, but what we're really going to talk about today is Dash. Okay, so Dash is a protocol for delivering streaming video. And the problem it's intended to solve is that network conditions can change suddenly, right? 1 second you can have a great connection. Next second it's like, oh shit, what happened, right? And Dash is designed to keep the video playing regardless of those kinds of changes. So I'm just going to walk through it. Okay, so this is Dash. The first part of Dash is videos are encoded to multiple levels of quality, right? So for example, you might have highest, high, medium, low, and lowest, okay? And the highest could require that much data. I'm gonna stack it like it's a little bit. High maybe requires that much, medium, that much, low, not much, lowest, not much. Okay, so height indicates how much data is required for that particular segment. So suppose you are walking along. Okay, so here we're going to look at the data rate or connection strength, right? Connection quality, how much data you can send. And here is time, right? So you're walking along. And at first, your network connection is great. Everything's happy. You're just la, 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 la. And then suddenly you walk and boom, there's like a big building between you and the cell phone tower. Hardly anything's getting through. Your connection crashes, right? It's like that for a while until you get out from behind the building, and then eventually your connection improves and you're back to where you were being happy. Well, what's going to happen initially, you're going to be getting segments like this, right? Because your system can handle them, right? You have great connection, whatever. As it sends you high quality segments and your connection speed drops, what's going to happen is that your buffer will start to get depleted, right? So make a mark here, buffer depletion. And when the buffer starts getting depleted, every time your device is saying back to YouTube, hey, I'm ready for the next segment, it's also including some information about the state of the buffer. And if your buffer is getting depleted, then YouTube's going to say, oh, we're sending you more data than you can really handle. So it's going to dial it down. It's going to start sending you eventually medium-sized ones. And if that still goes through and eats the buffer away, right, they keep on getting slower until maybe you finally just YouTube says, okay, you can't handle much here. Why isn't this? There we go. Come on. All right. Maybe YouTube says, okay, this is the best we're going to do today, and starts sending you these low quality segments, right? And maybe that's the most your system can support. But eventually, if they keep sending you low quality segments and the connection gets better, at some point, YouTube's going to recognize, oh, I see your buffer is again accumulating. Buffer restored, okay? And at that point, YouTube says, okay, great. Now I can send you better quality segments. And if I send you better quality segments and the system buffer keeps on getting better, right? Eventually, we're back to where we wanted to be. Okay, so that's how Dash does it. It basically says at any given point in time, I'm going to give you about the best set of packets, the best video segment that your system can handle. And the focus here is making sure that the video keeps on playing, right, rather than stops, because YouTube has figured out that people would rather watch a shitty, low quality video than wait a couple minutes for their video play to resume. All right. Last couple things, open and closed source. So some of this stuff, if you're interested in the architecture, fine. But I just want to mention open and closed source software. So up here, when we're talking about Dash, we mentioned that it is an open source. Oh, I thought I did in the slides. Maybe I didn't. Okay. Dash is an open source protocol, right? Basically, the source code for it, the source code is the code that humans write. Open source means that anybody can look at it, right? It's open to the public, basically. So that means two things. Number one, anybody can see the source code, see exactly how the program was written. And number two, anybody can use the source code for free, right? The downside, such as it is number three, if you do build something off of an open source platform, you can't sell it, right? It's like, You got this big free thing from some nice people, and then you put a little extra feature on it, and then you're going to try to sell it when, other people did most of the work. So there's a standard licensing process for using open source code. Other examples of basically effectively open source in the real world, things like Wikipedia. There was a real wave about 20 years ago where a lot of tech people were very excited about what they thought would be an open source code revolution. And if you were here taking classes, you could have heard a lot of IT and CS type people talk about, oh gosh, this is going to be the whole future of the world. Well, needless to say, open source code is a thing, right? But there's a lot of proprietary code out there as well. And the reason is, it's hard to make money off of open source code. And most of the time, if you want something to be done well and on time, you got to pay people to do it, right? So open source works well if it's an interesting project that a lot of people want to be involved in, and somehow people have figured out a way to make money on it. Anybody ever heard of the operating system Linux? Probably, yeah. Linux is open source, right? They can't sell it because it's open source. So the way they make money is they sell training services for it. All right. There's people who do that. And the way they get programmers is that everybody knows what Linux is. And so programmers who become, part of the process of building up the next version of Linux, they can put little bullet points about that on their resumes and say, yeah, I participated in such and such version of Linux. You can look me up. Here's my account. I've done good work. So a lot of people have figured out how to make that personally useful to them. There's other things that, even though they're open source, the projects are undermanned, underfunded, whatever. You can find a lot of things where people are trying to recreate old video games, right? From the 80s, 90s, aughts, whatever. And they say, wow, yeah, we're going to make an open source of, such and such video game we used to love, because those manufacturers, they won't give us the source code. They won't, release the source code for the game into the public domain. So we're going to try to make a clone of it. And those, even though they have people that are interested, right? It's like a hobby project for a relatively small pool of people. And those things typically take several years to get done, if in fact they ever get done. So anyway, open source, closed source. Closed source, of course, is proprietary code. So the example I say is Microsoft Excel. Obviously, there are many other kinds of proprietary code out there as well. With closed source code, you can make changes to it, right? But those changes have to be implemented as modules or add-ons that you can bring in. With open source code, you can actually go in and, make your own version of how that stuff works. You have a lot more control. All right. Anyway, last thing, security pros and cons. So a lot of what really fed the excitement about open source is there was a sense that security of open source code would be a lot better, right? And in some cases it is, right? With Linux, it's a famously very stable operating system because you have a lot of skilled programmers looking at it, and you have a lot of people with, lots of eyeballs looking at it. And it's open to the public. So if there's a problem in there, chances are anybody can spot it, right? Microsoft, on the other hand, you look at Windows, the old saying, never buy a new edition, never buy a new edition of Windows in the first year. Yeah. With that, Microsoft, their programmers are good, of course, but there are fewer of them and they're on a tight schedule to get stuff done. So they're going to make some mistakes. So there was a lot of excitement about, security of open source code in particular. But again, same thing applies, right? If you have a project with a lot of people involved on it, yeah, it's probably going to be pretty good. But the number of humans who are skilled at programming is pretty finite. And, if they're all on one project, they're not on the others. So, all right. Seems like a good break point. All right. Anyway, let's do 13. Relationship between jitter and latency. All right, is that everybody? You all got your answers in? All right, I'm gonna call it. Okay, correct answer. Good, see? All right, that's good. Yeah, 47%. Jitter is variability of latency. All right. Well, it's been a hoot. We'll see you next time. Have a good weekend. Yep. What's happening?